Hi, everyone. Today we're going to talk about combining the methods of conservation of momentum and conservation of energy in the same problem. Now we're going to start using conservation of energy more common and more often as a method to navigate problem solving. And these next several problems are going to have to do with using energy and momentum to solve one problem. So we will start with this one where we have two masses moving towards each other and there is a spring between them. Okay, so we've got block M1 equals 1.60 kilograms and is initially moving to the right at 4 meters per second on a frictionless horizontal track. It collides with a massless spring attached to a second block of M2 equals 2.10 kilograms that is moving to the left at 2.5 meters per second as shown in figure A. You can see that right there. The spring constant is 0.6 kilonewtons per meter, and the collision then begins to slow the blocks down as shown in figure B, as you can see right here. Oh, there. You can see that they are starting to slow down. It was originally 4, now it is 3. Now, part A asks us to calculate the velocity of block 2 at the instant block 1 is going 3 meters per second after it has slowed down. And part B, determine the distance the spring has compressed at that instant. So what we'll do first is we're going to solve using conservation of momentum to start with, right? So we want to know first, let's get our givens. Okay, so we've got M1 is, what is that, 1.6 kilograms. M2 is 2.1 kilograms. V1 initial is 4 meters per second. And V2 initial, I'm going to say that is the negative direction of 2.5 meters per second. Then V1 final, it has slowed down to 3 meters per second, and we don't know V2 final. We do know the spring constant as 600 newtons per meter. You're going to need to modify that, right? That was 0.6 kilonewtons per meter. I believe that's everything, right? Yes. So now we need to find V2F, then we need to find delta X. Okay. So first, what we can do is we can use conservation of momentum to find V2F. So we've got M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. The only unknown we have is this one right here, and it's the one we're solving for. So all you do is some algebra, plug and chug. You've got M1 V1 initial plus M2 V2 initial minus M1 V1 final, all divided by M2. That'll give you V2 final. So let's put in those numbers. We've got, let me move you over there. So we have 1.6 times 4 plus 2.1 times negative 2.5. Remember, don't forget your negative. Minus 1.6 times 3, all divided by 2.1 equals V3F. And when you do that math, that should come out to approximately 1.74 meters per second. Okay, so that is part A. Whoops. Mislabeled that. That should be V2F. So the velocity of the second block after they collide, it was initially going negative 2.5. Now it's going negative 2.74. Now let's do the other one. We need to find the delta X. Right? We need to know how far has that spring compressed at that instant. So this one we can use conservation of energy, right? And momentum has nothing to do with spring compression. So to do our conservation of energy, it's all on a flat surface and it's a frictionless surface. So we're just dealing with kinetic energies. You've got K1 initial plus K2 initial equals K1 final plus K2 final plus the potential of the spring. You could also say there's initial spring potential and you call it your ZPL. So to find the potential of the spring, you take K1 initial plus K2 initial minus K1 final minus K2 final equals that final spring potential. Now, we'll have to expand all this out. We have 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared minus 1/2 M1 V1 final squared minus 1/2 M2 V2 final squared equals 1/2 K delta X squared. Bad K. Here we go. So there is a 1/2 on everything. Get rid of the 1/2s to make this math a little bit easier. What we'll do is we will divide by K, right? Divide by K, and then take the square root to get our delta X. So we will take, I'm going to go ahead and use numbers. I'm running out of space here. So we've got 1.6 times 4 squared plus 2.1 times negative 2.5 squared minus 1.6 times 3 squared minus 2.1 times negative 1.74 squared, all divided by 600, all under a square root. And if you do that, you will get an answer of 0.173 meters, which is 17.3 centimeters for your delta X. Now that is a really big compression for a spring. If that spring was, I mean, it's got to be longer than 17 centimeters, which is over 6 inches long. So that's a really big compression, a really long spring. But that is how we can use conservation of momentum and conservation of energy in the same collision. They're just asking different questions, right? So an interesting way to go about that. Now what we're going to do is it's going to ask us one question. Calculate the speed of a bullet, right? But we're going to need energy and momentum all together to find that one speed. Okay. So what we have is we have a 1 kilogram block released from rest at the top of a 40-degree incline with a coefficient of kinetic friction of 0.22. When it has fallen a vertical distance of 1.5 meters, a 15-kilogram bullet collides with the block along a path parallel to the slope of the incline and brings the block to momentary rest. Draw the situation, then we'll calculate the speed of the bullet at the moment of collision. So we have our slope, we have a block traveling down the ramp, and a bullet coming to collide with it. Okay. This block drops, was that 1.5 meters? Yeah, 1.5 meters, and then it's going to come to a stop, right, once they collide. We are also going to assume that the bullet stays in the block after they collide, making this a perfectly inelastic collision. Okay, so let's get our givens before we start this. We've got an M1 of the block is 1 kilogram. M2 of the bullet, we've got 15 grams, so that's 0.015 kilograms. V1 initial. So this is going to be kind of tricky. So there are two parts to this collision, right? We want the speed of the bullet at the moment of collision. So that is our goal. However, we have two parts. Okay, there is the drop of the block, right, as it slides down this friction surface. And then we have part 2, which is the actual collision, right? So when I'm writing these down, I'll color code them. That would be easy. 1 is in blue, 2 is in green. So we've got the V1 initial for part 1 is rest, then V1 final, we don't know. That would equal V1 initial for the next step, though, right? We do know that V1 plus 2, once they collide, is 0, right? They combine together and they come to rest. Let's see, what else do we know? We have the coefficient of kinetic friction of 0.22. We have theta is 40 degrees. Oh, right, and a height of 1.5 meters. Okay. All right, good deal. So what we want to do is we want to calculate the speed of the bullet at the moment of collision. So before we start planning this all out, let's see what does that take. So if we want to look at the speed of a bullet during a collision right off the bat means use momentum. Okay, so we will use conservation of momentum. We have M1, V1, I'll do this in green because I was already doing that. M1, V1 initial plus M2, V2 initial equals M1 plus M2, V final, right? Which is that right there. That is 0. So since that is 0, we can actually get rid of it, right? So then we have M1, V1 initial plus M2, V2 initial equals 0. So what we want is the speed of the bullet, right? That's what it asks us for. However, we do not have speed of the block as it comes to the collision, right? We have that it starts at rest, but we don't know how fast it's going after it has slid down that vertical height of 1.5, right? So since we need that, let's go over to a conservation of energy and see if we can find that. So dead giveaway, right? It gave us a vertical height. That's a giveaway that we need to use conservation of energy because gravitational potential energy only uses vertical heights, right? So that's going to be a giveaway. What we'll do here is we will look at this blue spot right here, right? The part 1. So I'll do that in blue. I've got it all color coded and everything. So part 1, we have gravitational potential. We have kinetic energy. Then you've got gravitational potential and kinetic energy in the final. And then you've also lost some due to the work of friction. So we will say that at the bottom, that is the ZPL. We know that it starts at rest. So we have a UG naught equals KF plus work done by friction. That work done by friction is going to be tricky, right? If we look over here, let's see, if we have a block on an incline, normal is coming off at an angle, while mg would be straight down. So if we look at the components here, that is your angle theta. So normal will actually equal mg cosine theta if you look at that triangle there. And then the distance, I'll actually get another triangle so we can look at that. The distance, we know vertical drop of 1.5. The theta is 40 degrees. If we want this distance here, if we took sine 40, that is opposite over hypotenuse. So D would be 1.5 divided by sine 40. So we've got D, we've got N, we can use the work of friction. But what we're really looking for here, remember, is this red star, that V1. So we're looking for V. We've got M1GH equals 1/2 M1 V1 squared plus mu M1G cosine theta times 1.5 divided by sine theta. M1s can cancel out. And we want to solve for V. So we've got, see, we have GH minus mu G cosine theta times 1.5 divided by sine theta equals V1 squared over 2. What we'll do is we'll multiply by 2 and then do a square root to get this down to V1. Okay, so let's put those numbers in. We've got the square root of 2 times 9.81 times 1.5 minus 2 again times 0.22 times 9.81 cosine 40 degrees times 1.5 divided by sine of 40 degrees. And this all comes out to, what was that? 4.66. 4.66 meters per second. That is our red star. Right? That comes up here. So if we want to, so that's the velocity of the block as it's coming in for that collision, right? It has dropped a vertical distance of 1.5. So at that point, it's now getting hit by the bullet. So we have, if we want to solve for V2, you can subtract everything over and divide. You've got V2 initial equals negative M1 V1 divided by M2. So you've got negative 1 kilogram. That velocity we just solved for is 4.66 divided by mass 2, which is 0.015. And that velocity comes out to about negative 310.67 meters per second. So about 311, right? So that is the velocity that the bullet must be going if it's going to stop this 1 kilogram block in its tracks. Right? So you can see there, what I start with is finding, seeing what method we want to use to get the answer. Then you notice you're missing something. So then you have to go get that, whatever you're missing, right? Go get your something. Okay. We will actually continue that problem here. We've got the same system. Now I want to bring the block all the way back to its initial position at the top of the incline. What speed does the bullet need to have at impact, and how do the two speeds compare from these scenarios? So let's get our givens all over again. You've got M1, M2. Let's see. We don't need to worry about how what's going when the block falls, right? So here, right, we have block, bullet, and it goes right back to sit up top, and then it's going to come to rest, right? Forgive the sloppy drawing there. So we have V1 initial is 4.66 meters per second, right? That's at the collision, right? Yeah, so we're going to have the exact same scenario that we did before, right? You're going to have this rise of 1.5 meters, but you're also going to have one, that's the collision, and then part two is going to be as it's rising up to the other part, right? So I'll actually color these just like I did before so that we can try and keep these straight. So you've got V1 V1 initial is 4.66 meters per second. It actually wants us to know V2 initial. Okay, that is what we're shooting for, right? That is our goal. Then what we'll need, here is our crossover, right? The V1 plus 2 final, that will equal the 1 plus 2 initial as it's going up the ramp. Then we know that V1 plus 2 final will be 0. What else do we know? We know that theta is 40 degrees, kinetic friction coefficient of 0.22, and the height change of, again, 1.5 meters. So complicated color codes, I know. So let's work on seeing the method we want to use to solve this problem. What speed does the bullet need to have it impact if it's going to do that? So first, if we want to know the speed it has at impact, again, this is talking about impact at collision. So that's got to be conservation of momentum. So you've got M1 V1 initial plus M2 V2 initial. That is what we want. That equals M1 plus M2 V final. But that V final is not 0 this time, right? Now we know that it's going to be moving. However, we don't know how fast it's going to move, right? That's the one that we're missing. This is your red star, right? So what you'll need to do here is find out the velocity it takes this bullet block combo to slide up a frictionless surface and stop right at that point. So you've got a vertical description here. We have friction. We can do this using conservation of energy. I'll use green because I used green on the color code over there. So we've got a COE. Okay, you've got UG naught plus K naught equals UG final plus K final plus work done by friction, right? Now remember, this also has, this starts with the bullet in the block and ends with the bullet in the block. So we don't have to worry about two different masses, right? Everything's going to be an M1 plus M2. Let's call this starting position ZPL because it's at the lowest point. We will call this stopping at rest, so we can get rid of that as well. So what we have here, if we want to know the velocity that it takes, we need V naught, right? So this is what we're shooting for right here. So you've got, it's already solved and set up for us there. So you've got UGF plus work done by friction. Let's expand this out. You need 1/2 M1 plus M2 V naught squared equals M1 plus M2 GH plus mu. We also have, whoops, same scenario that we had before, right? For normal and for the distance, right? So normal will again be mg cosine theta, but that m is going to be m1 plus m2. And then that distance again will be 1.5 divided by your sine theta. Just the same system, right? Same system, same setup there. So you've got mu m1 plus m2 g cosine theta. Darn, don't you hate it when you run out of space? Move you over. Then, so that's your mu, that's your n, then your d, the distance, is 1.5 divided by sine theta. Okay, now m1 plus m2, that's gone. If you want to isolate your v naught, you multiply by 2 and take the square root. So v naught will equal the square root of 2gh plus 2 mu g cosine theta 1.5 divided by sine theta. Looks very similar. If we actually look at that, compare it to the previous problem, the only difference is this. That negative right there is the only difference between these two calculations. We have a positive this time. But you've got V naught equals square root of 2, 9.81 times 1.5 plus 2 times 0.22 times 9.81 cosine of 40 degrees times 1.5 divided by sine of 40 degrees. Now, I know that when you see that cosine and divided by sine, you want to simplify that. You can, but when I put that in my calculator, I kept getting it wrong when I simplified that using trig. So I had kept the cosine and sine separate, and I kept getting the consistent right answer there. So let's see. We have all of that. If you put that into your calculator, you will get 6.094. 6.094 meters per second. And that is the red star that we were looking for. Okay. That is the velocity of the block-bullet combo after the collision and as it begins moving up that incline, right? So now that we've got that information, we can finish this problem. Let's solve for V2 V2 initial. So you've got V2 initial equals M1 plus M2 times V final divided by, you got a minus M1 V1 initial, then divide by M2. So all of these numbers, you've got, let's see, it's 1.015 times 6.094 minus 1 times 4.66, that's right, divided by 0.015. So the speed of the bullet here is negative 723 meters per second. Now, the reason you might think that you're getting the wrong answer if you put that in your calculator is because I made a goof. This 4.66 right here, this is going down the incline, right? This is the velocity of the block as it goes down the incline. This 6.094 is the velocity of the block-bullet combo as it goes up the incline. So this is supposed to be negative because we've been using down the slope as positive and up the slope as negative so far. So that was my bad when I was writing those numbers, but there you go. You will get negative 723. It also asks you to compare the speeds from these two scenarios. So you've got negative 723 to push the block all the way up, and then you've got 311, approximately 311 to stop the bullet where it's sitting still. So you have over double the velocity of the bullet if you want to push it back up to its original point. A much bigger difference. It's not just double. Okay, this is our last one. We are shooting for clever title, but I'm blocked. So we've got a 20-gram bullet fired horizontally into a 1 kilogram block of wood, resting on a horizontal surface with a kinetic coefficient of friction of 0.25 and a static coefficient of friction of 0.29. The bullet goes through the block and comes out with a speed of 250. We've never done that before. So the bullet goes through the block and continues going. And then the block travels 5 meters before coming to rest. So what is the initial speed of the bullet? All right, so let's see. We've got block, block. Okay, so you've got bullet goes through the block and causes the block to travel 5 meters, but the bullet is continuing to move at 250 meters per second as it goes. Let's see, that bullet is 20 grams. This is 1 kilogram. The surface also has friction. It's 0.25 for kinetic and 0.29 for static. It's all flat, so no theta. Okay. So what is the initial speed of the bullet? Well, we know the speed of the bullet after. We know the speed of the block before. So this would be a conservation of momentum. So we'll do conservation of momentum. You've got M1 V1 plus M2 V2 equals M1, V1. Oh, don't forget your finals and initials. Plus M2, V2, final. We know V2 final, right? Let's see. V2 final is 250 meters per second. V1 initial is 0 because it's sitting still. So this is what we want, right? We want the speed of the bullet initially. This is all 0 anyway. But we don't have this. This is the red star right there. So we need to find out how fast the block was moving after the bullet went through it and then it skidded for 5 meters. So that is where we will go use conservation of energy. So this is the block, right? They didn't combine, not perfectly inelastic, but this is where they combine this is where they don't combine, and this just the block. So we just need to deal with one mass, which is nice. It's all on a flat surface, so there's no gravitational potential. So you've got K naught equals K final plus all the work that friction is doing. It is sitting stationary to start, so you really just have the negative work done by friction equals Kf. And remember, we're solving Kf. We want the velocity. So if we have negative mu nd equals 1/2 m1 v final squared. Let's see, our normal force, we are sitting on a flat surface. Okay, so normal will equal mg. The distance was given to us at 5 meters, so we have all of that. So you've got negative mu m1 g times d equals 1/2 m1 vf squared, right? The m1s can go away. So to find vf, you multiply it by 2 and get a square root. Uh-oh, there's a negative there. Why is there a negative there? I don't remember that negative being a problem. Oh, because I'm being dumb. That's why. That's why. It is not initially sitting at rest. It is finally sitting at rest. Because this kinetic energy, I was thinking about the collision. COE can't do a collision. Silly Pentecost. So initially, the bullet pushes the block, right? So it is moving initially, but finally it comes to rest 5 meters away. There it was. So it's already set up for us. You've got the 1/2 m1 v naught squared equals mu m1 g times d. There we go. That looks much better. All right, so multiply by 2 square root. You've got v naught equals 2 mu g d square root. That's the square root of 2. The mu changed on us. So here, do we want to use kinetic or static? So static, you almost always use static if you're trying to figure out, does the object move? For example, if the question was, bullet fired into a block, the bullet goes out the other side of the block, does the bullet move? Or sorry, bullet goes through the block, does the block move? Then you could use static, right? But since we know that the block is going to move, you can usually ignore static. So we're going to use kinetic for this. So that would be 0.25, 9.81 times 5 square root. Okay. So that V naught is going to equal 4.952 meters per second. And that is our red star. Right there. Okay, so the velocity that the block starts moving as it scoots across that friction surface is the final velocity the block has after the collision, right? Okay, Good deal. So if we come back over here, remember this is the M2 V2 initial. That is the velocity of the bullet that we're looking for. That's what the whole problem asked us to find. Then we've got M1 V1 final. That is the momentum of the block after the bullet has gone through. Then you've got M2 V2 final. That's the momentum of the bullet after it has gone through. So solve for V2 initial. You've got M1 V1 final plus M2 V2 final, all divided by M2. So let's get our numbers in there. Let's see, we've got 1 times, we just solved for that velocity. That is 4.952 plus 0. This is a new bullet, right? Yeah, 0.02 kilograms. And it is going at 250 meters per second divided by 0.02. And you should get about 500. It is approximately 498 meters per second. Okay, so I know I made a couple mistakes, so I apologize if that was adding to your confusion. But what we have here is that bullet goes through the block and out the other side. We know the velocity as it leaves, but we don't know the velocity that it hit the block with. But we do know, just with the information, that the block was sitting at rest and skids 5 meters and then stops. Just with that information, we were able to determine the rest of the information. We were able to determine the speed of the bullet as it hit the block. And we also needed the coefficient of friction for that as well. But that's how you can set up a conservation of momentum problem if you need to find something else using conservation of energy. That wraps up our video here. We're going to continue on through this unit of linear momentum and center of mass in our next video.